I'm going to try to answer two questions for you today. What is mathematics, and what do mathematicians do? If we ask someone on the street, what does a mathematician do? What sort of answers might we get? Some might say they do calculus or algebra. Some might mention some big problems like the Riemann hypothesis or Fermat's last theorem. Some might say mathematicians just add numbers all day. If I'd been asked, I would have said something like they sit down at their desks with pen and paper and work on some interesting problem or new idea, which is a fine enough answer if you don't want to learn how they do it yourself. It's a bit like a programmer saying, I just sit at my laptop and type. The problem, in my view, is that it's actually pretty hard to explain what a mathematician does because I don't think people know what mathematics is. You may think that mathematics is this abstract logic game for the nerdiest of nerds, but actually, it's a way to take our ideas from reality, pare them down to their barest bones, and run experiments on them, at least in my view. And with this definition, mathematicians are the people who run this process on mathematical ideas. Lots and lots of mathematical ideas stretching back thousands of years. Now, I don't pretend that these are the definitive answers to these questions. Instead, I want to present what I think could be an interesting way to approach mathematics as a whole, especially if you, the viewer, are interested in trying this mathematics thing and are just poking around at the edges right now. So, pretend you're a mathematician, someone who's enthusiastic enough about mathematics that they start playing around with it. How do you even start playing around with mathematics, though? Well, there's a lot of ways, but I think one simple way is to ask a question about math and try to answer it. But how do you even find a question to ask? And how do you try to answer that question once you have it? In this video, I'm going to try to cover what I think are 3 simple steps to doing some mathematics. 1. Pick a question to ask. 2. Run some experiments to try to answer your question and see what you find. And 3. Check your work and tell others your results. This is also known as peer review. This may not seem like a mathematical approach at this level, but I hope things will become clearer as we go along. For now, the stage is set. Let us begin. Part 1. How do you get a question? So what I'm going to do is, instead of trying to ask you to ask a question, which would be rather difficult considering this is a published video, I'm going to pose a question to you. Let's start with something very familiar to us. Our Earth. Our Earth is a sphere, or close enough to it for our purposes. But if you take a sphere, draw on the lines of latitude and longitude like we have on Earth, what can we say about this object? Well, let's try drawing a triangle. We can draw a triangle with one of the sides on the equator, one at 0 degrees through Greenwich in the UK, and the third side going through 90 degrees east through Western China and Bangladesh. Now you have a triangle, but it has 3 right angles. There's one right angle at the North Pole between 0 degrees and 90 degrees, and there's 2 at the equator between the equator and the lines of longitude. This is a 270-degree triangle. How can this be? Didn't we learn in school that triangles always have 180 degrees, no more and no less? Why are spheres different? Are there any other differences? Can we learn more? The point I want to emphasize here is that mathematicians don't ask arbitrary questions. We're not just playing random games. We take ideas from reality, from our previous knowledge, and from recent discoveries and research, and we ask questions about what we know and what we think we know. These questions could be things like, do we have a solid understanding of a mathematical technique or proof? Can we ask questions that develop these techniques further? Can we use these techniques, our old ones and our new ones, to solve some problems, some questions that we've had for some time, maybe. Can we even answer the questions that we have? And especially with this question, what happens when you try to draw a triangle on a sphere? Does something break? The motivation for this question came from our real life, our lines of latitude and longitude, our GPS coordinates, and our planet. It didn't come from some thought experiment where, what happens if we make a triangle that has 3 right angles? Now, a lot of our mathematics is thought experiments, but my point here is that we draw an incredible amount of inspiration just from our everyday life. We took ideas from our real life, the Earth and its lines of latitude and longitude, and turned them into a question in mathematics, a question about spheres and triangles. What we observe in real life and in older math observes what we try to turn into new math. And that math can run away from that starting point, especially from real life. But almost always, if you look back far enough, there is some starting point that we built all of this new mathematics from. And once we have that starting point, we're off and running. Part 2. How do you run an experiment? Now that we have our spherical geometry, our weird triangles on spheres, the ones with 3 right angles, or at least ones with more than 2 right angles, more than 180 degrees. What do we do with this knowledge now? Well, as I said at the beginning of this video, the way you do mathematics at this point is, once you have a question, you start running experiments on your question and see if those help get you towards an answer. In this case, we have spherical geometry, but we also have our regular flat geometry from school. One simple experiment we could do is compare the new spherical geometry with the old flat geometry. But another question pops up. What exactly was the old geometry from school? Well, one way to describe that old geometry is as the geometry of flat pieces of paper. Usually we call this Euclidean geometry, named after the ancient Greek mathematician Euclid. He's considered one of the greatest geometers, largely because he was one of the oldest, earliest ones, and also because of his most famous book, The Elements, which essentially is him writing down as much geometry as he could and turning it into a treatise on how do we prove all of these cool things from simple ideas at the bottom. At the beginning of The Elements, he starts with some definitions. What's a point? What's a straight line? What's a triangle? What's a circle? And then he defines some common notions. Things like, if you have 2 line segments that start and end at the same points, they're the same line segment. A equals A. Simple stuff like that. Euclid also starts with some postulates, what we would call axioms today. Axioms are unchallenged assumptions that we use as starting points and then build arguments and turn those arguments into things like theorems. For the rest of this video, when I'm referring to postulates, I'm specifically referring to Euclid and his postulates in The Elements, and when I say axioms, I mean general unchallenged assumptions in mathematics. So, let's take a look at Euclid's postulates, because this is actually going to be pretty important for our experiment. The first postulate is this: a unique straight line can be drawn between any 2 points. The second postulate is that any straight line segment can be extended indefinitely. The third postulate is a circle of any radius and center can be drawn on the plane. The fourth postulate is that all right angles are equal to each other. Fair enough. And the fifth postulate is, given a line and a point not on that line, there is a unique line through that point that does not intersect with the other line. Heavy asterisks all around. I'm skipping a lot of nuance and discussion. Now, a quick note about that fifth postulate. Yes, it is wordier than the others. That's going to be a point for later. And what it's actually saying is that in our flat Euclidean geometry, there are parallel lines, but there is one unique parallel line through any point you care to name.